Okay, let's begin. So in the last class we looked at the need for a common mode feedback, right? And the reason why we need a common mode feedback was in a fully differential op amp you have basically two current sources that are biased independently, so you'll not be able to define what the intermediate voltage is. So you need to have a separate feedback loop that senses the output common mode and fixes one of the current sources. And we saw basically two variants yesterday. So one was straightforward. I'll sense the output common mode using two resistors like this and directly connect it to the gate. Now in this, the common mode is set to some process dependent voltage that is not under your control exactly. And the second variant we looked at towards the end of the class was this, wherein we use a separate op amp here to sense the common mode and fix it to the required common mode reference we want. And we basically saw in if you draw the common mode half circuit, this essentially looks like a two-stage OTA. So to get a good phase margin, we will have to add this Miller cap, and this is how it looks like in the complete picture. So let me copy this and continue. Okay, right. So I'll use the same color so that we don't have an overload of colors. Okay, cool. So now one thing is, here we know that we have to use an OTA, but I directly used an NMOS input pair for the OTA, right? So do you think using a PMOS input pair is better? That is, see, the OTA, it is for sure that we have to use an OTA and compare the common mode with the reference. But here I have chosen the input transistors to be of NMOS, right? My question is, what if I use a PMOS input OTA like this? So this is my PMOS differential pair, and then the current mirror load here. And this is also the same OTA, right? So do you think this will be better, or do you think this is a better choice? Why?
Because is VDD minus VSG.
Okay, so others? I mean, with respect to using an NMOS or a PMOS input OTA, what is the, I mean, with if you
basically like
what will change?
In two stage we used to do like the same configuration and then we used to use PMOS.
Yeah,
same.
right. I mean, see, the point is, if you have a OTA with respect to small signal using an NMOS or a PMOS, there is virtually no difference. So what is the difference?
The gate voltage.
DC bias voltages. Okay. So at the input it's all okay because we are going to sense some common mode which is close enough to VDD by 2. So we can either use NMOS or PMOS at the input. But what is crucial is this output here. Here it's connected to the gate of a PMOS, isn't it? So if I use this guy, if I use a PMOS input, I'll have to go and connect it like this. So this will be some VDD minus VSG, and this is equal to the gate to source voltage. So it's not so compatible. But if I use an NMOS input, the voltage here is basically VDD minus VSG. It is easily compatible. Like you told, we saw the same thing when we had two-stage Miller OTA, right? So if we had an NMOS input for the first stage, we saw for the second stage using a PMOS input pair was a better choice, simply because the voltage levels are compatible. Okay, so here it makes more sense to use an NMOS input pair OTA, again simply because of the fact that the gate voltage here will be at a, the output voltage will be at a level that is compatible with this gate voltage. So, and as we know, to avoid systematic offset, what should I ensure here?
Current density.
of all the PMOS transistors, the current densities must be equal. Okay. If you don't ensure the current densities are equal, then the signal voltage here, that is the common mode, will not be exactly equal to your common mode reference you want. It will be equal to this with some offset voltage, and we calculated what that offset voltage is and so on. Okay, cool. So now, okay. So again, change this guy once. Great. So now here there is one issue that could arise, which is the following. So we haven't considered the effect of the parasitic capacitor at the input of this OTA. Okay. So if there is a parasitic cap, say it's some gate capacitance CG, what do you think will happen now? Sorry? Yeah, we'll have more poles. So what will happen finally in the feedback loop? I mean, you are right. This additional cap is going to introduce an additional pole. So what can you comment on the stability or the phase margin? Phase margin you expect it to reduce. Okay, because I mean in our design, in the two-stage OTA design, we never considered this guy at all, isn't it? So if I were to draw at a block level, I'll have the first stage OTA like this. Okay, this is the first stage. So this guy constitutes the second stage. Okay. And at the output of the second stage, I have this resistor. In common mode, the two resistors come in parallel. So I'll just have RCM by 2. I'll move this up. So I'll draw the resistor like this. And this resistor is finally connected back to the input of the first stage. So this is what we have. Okay, this is my VCM ref. Oops. And of course we have put the Miller cap around the second stage like this. It's fine. Now here we are saying that we are going to have an additional capacitor, say CG, at this node. As usual, you know, this is now going to introduce a third pole, this resistor and a capacitor. So this is going to decrease your phase margin. Without going into a lot of calculations, what do you think is the simplest thing you can do to counter this effect? Yeah, how do you add a 0? No, you can't add a resistor here. This is a parasitic capacitor. I mean, you're saying it right. We have to add a 0. But how can I add a 0 here? Ah, 0 basically provides a fast path. So how can I introduce a fast path here? Sorry? Why do you want to use a buffer? Okay, I mean, you also saw this in two-stage OTA, so let me rephrase it another way. See, the main issue with this capacitor is the following, right? If let us say the output changes suddenly, because of this capacitor, the voltage here is now going to take some time slowly and settle. So this introduces additional delays, and having excess delay in a feedback loop is a recipe for instability. So I don't want to have a lot of delay. I want the output here to respond quickly. So what can I do? Where should I add the capacitor? I mean, this is the network. Where should I add the capacitor now?
In parallel to the resistor.
Huh? In parallel to the resistor, like this. Is that okay? So now if I apply a step here, oops. Let us say now here I have the same step input. At t equal to 0 plus, how do you think the output will behave? At t equal to 0 plus, I mean, how does a capacitor behave? No, at t equal to 0 plus, it's open. Why? It acts like a short, right? I mean, loosely speaking, it restricts sudden change in voltages, so it acts like a short. So both capacitors now act like a short. So what do you think this voltage will be? It's basically the capacitive division, right? I mean, this is now a short circuit, very low impedance to say. This is in parallel with a resistor. So what will dominate? Only this capacitor will dominate. So this and these two guys. So essentially have a capacitive division between these two. So how will the output look like at t equal to 0 plus? It will jump instantly, right? And the jump will depend on the capacitive ratios and stuff. And once it jumps, then it will slowly do this. Okay. Now you see, right? Now when the input makes a sudden change, we do get a response immediately, right? Of course, this is not the final value to which you want the output to reach, but for with respect to stability, we don't want the loop to respond with the exact value we want. All we want is whenever there is some jump, I want my output also to rise in the same direction. Okay, as long as that is fine, the loop is going to be stable. I mean, this we saw when we discussed Miller-Auti also, right? I mean, the other way to think about it is, see, if I take this network here, we have R and C. So at very high frequencies, what is the phase from VI to Vout? At let's say 10 frequency to infinity, what is the phase of the output? Minus 90? Is that okay? I mean, see, at very high frequencies, capacitor acts like an open or a short? Short. Okay. So you can, to first order, we can say the output is roughly 0. If that is the case, what is the current flowing here? It's R and C. VI by R? So now this VI by R current flows into the capacitor. So output is approximately 0, but a better approximation is what? A current VI by R flowing into a capacitor. So what will be the output in Laplace domain? I mean, we have a current VI by R flowing into a capacitor essentially. Okay. Okay. And I mean, if you write in Fourier transform, we will move this quickly. In Fourier transform, it's basically VI by j omega RC. So the phase as t tends to infinity, this is as omega tends to infinity. Okay. So as omega tends to infinity, the phase is what? Minus 90. Okay, I mean, this was a problem, right? This capacitor was adding a phase lag and that was degrading your phase margin, right? Now let us say I add this new capacitor here. Okay, let's say this is some Cg. Now let us say this is some other cap C. Now as t tends to infinity, not t tends to, as omega tends to infinity, what is the output or the ratio V out by Vi? At high frequencies, again we saw, right, only this capacitor is going to dominate in this parallel impedance network. So we'll only have the division between the two capacitors, so it will be C by C plus Cg. So what is the phase here? 0 degrees, isn't it? So the idea is the same again. This additional capacitor is introducing a 0 and the 0 is countering the phase lag that you had originally, so that your phase margin kind of is okay. Is that fine? So this is the simplest thing you can do. You can basically add a capacitor in parallel with a resistor. So here you will have to add the capacitor here like this. Okay. So I'll call it CCMZ to signify that it introduces a 0. Okay. So this is our CMFB variant 2. Okay. So now in this network, in differential mode, what is the equivalent circuit? So in the differential mode, what voltages are 0? Yeah, this tail node is 0 obviously. What else? This guy is 0. What can you say about this guy? That is also 0. It's a constant voltage. Incrementally, that's also 0. So yeah, this is also 0. So basically this op amp is not in the picture at all, right? Both inputs are 0 and the output is also incrementally short. This is the output, right? Incrementally short. So incrementally speaking, this nothing, I mean in the differential half circuit, this doesn't come into picture at all. Okay. So how does the circuit reduce to? Tell me the half circuit. I have the PMOS here, its gate is grounded. I have the NMOS. Now this was our CCM by 2. So how does this come now? To output from the output to ground, you have this capacitor. What about the other guys? This is also ground, mind you, right? It's a common thing. So they will also come in parallel like this. Okay. Right? Now these capacitors, they are appearing at the output and loading it. That is something you cannot avoid, that you need for stability, right? Because you want the common mode feedback loop to be stable, so you can't get away with these capacitors. That is something you can't avoid. Now this resistor here is there for sensing your common mode, and that is loading your output and reducing your DC gain, right? Again, as we saw, to make this effect negligible, you can increase the resistance value, but that's going to take up a lot of area. So what do you think we can do to make sure that this resistor here does not load the output? Yeah, we can use a large value of resistor, but let us say you don't want to do because it's going to take a lot of area. What is the other thing you can do so that, see, I want the resistor here, but what I'm saying is I don't want the resistor to load this node. So how can I connect the resistor to that node? We'll have to add a buffer. Okay, fine. So I'll do that in the complete circuit here. So here I'll have to go and add a buffer. So I'll upload this video immediately, so it's okay even if you're not able to draw the circuits. Okay, I'll simply copy paste to save time. So now we'll have to add this buffer. What is the simplest buffer you know? Not common source, common drain, source follower. So I'll replace this buffer by a source follower quickly. So I'll probably take this, push it to the side. So here I'll have a source follower. The other output is also buffered like this. Okay, and we'll tap the outputs like this and feed it. Is that okay? Same thing. So instead of connecting the output directly to the resistor, I'm using a buffer and then connecting. Okay. So doing this will make sure that now the output side I'm not loading the resistor here, so my DC gain will not change. It will be same as before. Okay. Now, but note that let us say I call this VOM and VOP. If this node voltage is VOP, what can you say about this guy? No, not incrementally. Let's say, I mean, this is the DC potential. Let us say VOP. Sorry, this is, let us say, the DC potential VOP. What will be the DC potential here? How can it be same? If this also DC at VOP, then gate to source voltage is 0, right?
VOP minus VGS.
Right? So let me write that. Is that fine? I mean, this is going to be one gate to source voltage below that.
Yes.
Gate to source voltage of some NMOS, let's say at some current Ix. I'll not go into details. So similarly, this is VOM. So what will be this voltage? Same thing. So this is going to be VOM minus the same VGS at a current Ix. So remember, these two voltages are the ones that is getting averaged by the resistor. So what will be the average available here? By 2. So that is my common mode, required common mode, plus minus this VGS. Okay. So this is what is getting fed as the input to my OTA, and the OTA will try to make this voltage equal to this voltage. So in steady state, what we'll have is this. Okay. So if I have this source follower, my output common mode is not equal to the required reference voltage. It is equal to this voltage plus some VGS. So this is not something you want, right? So what is the fix, do you think? What do you think we can do? I mean, remember, this is something that we cannot avoid, right? We have to have the source follower if you don't want to load the output. So this is something you can't prevent.
VCM ref minus that.
Right? So if I basically add minus VGS here, we are okay. How can I obtain a voltage that is VCM minus VGS?
Put the same buffer.
We have to have the same source follower there. Okay. So now I'll draw that quickly. So this is. So instead of connecting VCM ref directly, I'll actually give it to a source follower like this, the same source follower. So now this voltage will be VCM ref minus the same VGS at the current Ix. So now my output common mode voltage be VCM. Okay. So this is what you'll have to do if you decide to use a source follower. You'll have to have the same source follower for the two outputs as well as for the reference that you are providing. Okay. So this will be our third variant. Right. Now, although this is nice, there is one issue. So what do you think could be a possible issue with using a source follower here? Remember, the source follower is directly connected to the output of my OTA. So we have seen before what could be the potential problem with having source followers. Say capacitance is not a problem. Something. Huh? Can you explain more? Yeah, I mean, okay, why? I mean, even when we discussing our OTA, I mean, we told that we can have an OTA followed by a source follower to have an op amp. But why don't we do this in practice? This source follower is going to limit my swing. Okay. I mean, and even otherwise, see, loosely speaking. So here, before when we didn't have this buffer, the output was directly connected to some resistors, right? Now the resistors themselves don't say anything about swings. We can have any swings we want. Now the moment you have a transistor here, we need to make sure the transistor remains in saturation. So this transistor will introduce additional constraints on my output swing, right? That's all. So the problem here is we cannot have a large output swing. So we'll have only a limited output swing here. Okay. So as long as your outputs are not swinging so much, what is that so much you can calculate, we can use this technique. Okay. I will also show one other thing that is commonly done. So this is our original circuit. So here, let me erase this cap, it's not relevant now. So what is this voltage? If I call this VOM and VOP, it's average of the two, VOP plus VOM by 2. So let us say this voltage is some Vx, okay, and you know what approximately what is this voltage equal to? It will be average of the two. I mean under some condition this will be exactly the average. Otherwise it will be the average of these two voltage plus something. But either is, let us say it is some Vx. Okay. So then can you tell me what is the current flowing here? Say I call it IA and both transistors are say MA and MA. Can you tell me the incremental current IA?
Is minus this upon 2 into GM.
IA is what? GMA
Into this both voltage subtraction upon minus
VOP plus VOM by 2 minus Vx. That's all. Fine. So I can rewrite it like this. What I'll do is this. I'll write it like this: GMA by 2 times VOP minus Vx. Fine. Both are same. Now let us say I don't want to. I want to realize this current as sum of two currents like this. How can I obtain a current which is GM times VOP minus Vx?
one of the input was GM.
What should I do? I want to have an incremental current which is some GM times VOP minus Vx.
VGS should be VOP minus.
My VGS should be VOP minus Vx. So I'll take a transistor.
By 2, right?
Why it's by 2? I mean GM is, I am taking the factor as GM. So if this is Vx and if this has a trans conductance GMA by 2, this is fine. Similarly, I'll do this. This is VOM, right? And this both source voltages are same. So I'll remove this guy. I'll go ahead and connect this. This is Vx. How can I add the two currents now? How can I add two currents?
VDD connect the.
I'll do this. Okay.
Yes.
Adding currents is straightforward, right? This current is GM times VOP minus Vx. This is GM times VOM minus Vx. So this is the sum of the two currents. So I need to ensure this transistor has a trans conductance GMA by 2. So let us say this also same transistor has GMA. Okay, so what I'll have to do is the following. Instead of having one transistor like this, I'll now replace with what we have. Two transistors. Here I'll have VOP, VOM. Okay. So now which means I don't need this guy. I am doing my averaging using transistors now, isn't it? I initially wanted the resistor to get the average of the two voltage, but now the average is obtained like this directly, right, using these transistors. So I don't need them. So I'll erase this, and this is how it will be. And remember, I want the GM of these two transistors to be half of this GM. Okay. So let us say this current here is some 2 times Ix. What will be this current? Ix. And currents here will be Ix by 2, Ix by 2. So if this transistor has a size W by L, how do you think these two transistors should be sized?
2W by.
No, I want half GM by 2.
WL by 2.
I should have half the widths. Okay. If I have half the widths, they are carrying half the currents. GM will also half, and that's what you want. You want GM A by 2. Okay. So now this is the other CMFB you can have. This is also widely used. So this avoids this, gets rid of the need for having resistor, and you can directly connect my outputs to the gates of the transistors. So we are not loading the output again. But again, now we are directly connecting the output to a transistor. So what can you say about the swings? I mean, the outputs are directly connected to the gates of some transistor. So this is also going to restrict my output swing. Okay. So again, with this you can't have very wide swings like you can have with the resistor. This will also have limited swings. So this will be our CMFB variant 4. Okay. So just to quickly summarize, we saw 4 techniques till now. One was to take 2 resistors, average it and connect to some gate voltage. Oops. Right, this was VOP POM, and this was directly controlling some gate voltage of a PMOS. That was the first thing we saw. Second thing was to take the average using 2 resistors but compare it with using an OTA and feed it. And then what did we do? We didn't want the resistor to load my output. So what did we do? We used a common buffer, no, common drain, not common source. So we used a common source like this and then put a resistor, and at last we saw instead of using resistors to average it, we basically used 2 transistors like this, and the averaging was done in current like this, right? So again, here in the first 2 things, the output is directly connected to the resistors. So this is going to load my output, but the resistors themselves are not introducing any constraints on how my output swings should be. So this can support a very wide swing, no issues here. Whereas in the 3rd and 4th, the output is directly connected to the gates of transistors. So here there is no loading, but what is the issue? This additional transistors are going to limit my output swings, so we'll have only a limited swings here. So this is the trade-offs in these. Is that fine? Now again, if you think about it, in all the 4 techniques, what we have done is the following. We have probably use this one maybe. In all the 4 techniques, we essentially assume that the NMOS current source is fine. We let it go independently and only tune the PMOS current. Now there is nothing sacred in tuning only the PMOS current. We can do the other way also. We can assume that my PMOS current is fine and go and tune my NMOS current. So everything we have done, we can also do by feeding back the signal to the gate of my NMOS also. Okay, but there are a couple of variants I'll show. So I'll first draw the circuit. Oops. So this is my diff amp. Okay. So again, I'm assuming that my PMOS current source is biased properly. So nominally it should carry a current of some I0 by 2, right? So I'll bias it like this. So let's say I have an identical PMOS. Fine. So this way the PMOS current sources are biased to carry a current I0 by 2. Now I'll go and tune my NMOS current. Okay. Now how can you control the current in the NMOS? What should I change to change the current in the NMOS transistor? Gate voltage. But current in a transistor, what does it depend on? Yeah, I mean if this is going to be acting in saturation to act like a current source, in saturation region, what does the current depend on?
VDS we are considering the.
I mean, assume that it's VDS is negligible, right? So what does it depend on majorly? Gate to source voltage or the overdrive voltage. So I can control my current either by controlling the gate, that's what we have seen, or you can also control what is the other voltage I can control here to change the current. I can also control my source voltage. Okay. So I mean, one thing again you can do is I will sense the output common mode and then use my some OTA to do this. But this is not a great idea because your source voltage here, you want it to be a large voltage or a small voltage?
Small.
You want it to be small. Ideally, you want it to be ground, isn't it?
And down.
But we can't have a ground in this case. So, but you want it to be really small. Else, you are unnecessarily losing out some voltage here that is going to restrict my output swings. Make sense?
Yes.
So it's not a great idea to use a OTA here. Okay. Oops, what's happening? But still we want to control my source voltage. So we have to connect something here that will have very small drop. Okay. And let us say the current in the NMOS transistor here is less than I0 by 2. Then what can you say about the output common mode voltage? The PMOS current is set to I0 by 2. I am saying the current pulling that is being pulled out is smaller than I0 by 2. So this voltage, what will happen to the common mode here? That will increase. Okay. So this is my common mode voltage. If the common mode voltage increases, I'll have to go and correct it. So what will I do to the current? I'll have to increase the current in the NMOS transistor, which means I'll have to increase the current in this guy. So which means what should happen to the source voltage?
Or decrease more.
Source voltage must decrease. Okay. So basically if this voltage increases, this voltage must decrease. So this basically is a 3-terminal element, right? So looks like we need to have a 3-terminal element, wherein if we have a positive increment in one of the terminals, we have plus delta V, I should have some minus delta V naught. So what is the simplest 3-terminal element you know that? It's a common source, simple transistor. Okay. So what you want to do is this, replace this guy by a single transistor like this. This should be my VOCM. Okay, and again now we have to obtain this VOCM. Instead of using some resistive divider to obtain it, we will take a cue from our previous experience and do the following. Oops. So I will have basically 2 transistors like this. Okay, just like how we did the averaging using 2 transistors in our previous implementation, I'll do the same thing. And as we mentioned, this voltage drop must be really small. So the drain to source voltage is small. So which region the transistor is operating in? It's operating in linear region. So it's essentially acting like a resistor. Okay. So again you can check if it's a negative feedback. So let's say the output common mode increases, this guy decreases, current in the transistor increases. If the current increases, this current will be more. You will pull out more current from that node, node voltage will decrease. So it is a negative feedback. But the actual voltage to which my output common mode is set, that is not very obvious here, right? We are not comparing the output to some reference and doing it. It is again set to some value, and to find what that value is, we have to write the current equations and then find it. Okay. So this as such is not a great circuit, but we can actually do one minor variation to make the output common mode equal to the required reference. And the idea behind it is the following. Take this. Now let us say these transistors are MC and MC. What is the nominal current flowing in these transistors? I0 by 2. Fine. So let us say I take an identical transistor MC. Let us say I connect its gate to the required VCM ref. Okay. And let us say somehow I force the current in the transistor to I0 by 2. And then let's say copy this drain voltage here somehow. Now essentially you have 2 identical transistors, right, having the same current. So what can you comment about this gate voltage in that case? It has to be VCM ref, right? I have two identical transistors, both are carrying the same current here. I am ensuring the source voltage is same, drain voltage is same, which means the gate voltage must also be same. That is the only possible solution this negative feedback loop will lock this gate voltage to. Is that clear? So this is the principle we'll use. So to achieve this, we need to do two things. We need to make sure, what do we have to ensure? In this transistor, what is the thing that we need to ensure? Current must be I0 by 2. And next? I mean, VDS should be same in the two. Right? I mean, we want to make sure this gate is finally at VCM ref. And for that to happen, even the drain to source voltage must be same. So these two voltages must be same. First thing is I need to pass a current I0 by 2. Second thing is make these two voltages equal. So first let's start with making the current I0 by 2. How can I make the current I0 by 2 here? Yeah, I already have a current here. Let's say make it flow here like this. Fine. But does it make these two voltages equal? No. So what do you think we can do? No, we can't connect them, right? Okay, think, right? So what is actually setting this voltage here? Sorry? This guy, isn't it? So let's say this voltage is some VB. What is this voltage? This current is I0, remember. This is VB minus VGS of the transistor at a current I0. So basically now I can't do this. So what can I do? See, this voltage is VB minus VGS at a current I0. I want to have a similar voltage here. I mean the same voltage here. I can have a same transistor, connect its gate to the same voltage, right? But one catch is there. See, if I have a transistor here, what is the current that will flow through the transistor? I0 by 2. Let me draw it clearly. Exactly, right? So if I'll have to connect this, if they both have the same gate to source voltage, this must be 2W by L and this must be W by L. Okay. Then for the same gate to source voltage, they will carry the same current. Then these two voltages will be identical. Now one last thing, we need to obtain this gate voltage for biasing, this voltage, right? And this voltage must be such that the current flowing in this transistor is I0 by 2. How can we generate this voltage now? I can do a direct connection like this, isn't it? Okay. So if I do a direct connection like this, now the current here is I0 by 2. Here the current is I0. They have the same gate voltage. Their gate to source voltages are same, so even their drain voltages are similar here. And that will ensure that my output common mode is equal to the VCM ref that I have supplied. Okay. So as long as these two transistors are identical and all these three are identical, my output common mode will settle to the required value, which is VCM ref. Is that clear? Now one other thing you can do is, see, this is just a biasing branch if you want to think about it. So let us say I don't want to burn the same current I0 by 2 in this branch also. What can I do? I mean the point is, see, I am also burning a current I0 by 2 in this branch which is there only for biasing. I don't want to, I want to burn a lesser current. What can you do? I want to burn the lesser current but maintain the same functionality as I explained. Okay, so if I just scale the current to some I naught by 2 times n, will it work? It will not work. What should I change in the circuit then? No. See, earlier let us say, what can you say about the sizes of these transistors? Huh?
Same.
All these three will be same sized. Right? Now let us say, what I am saying is, the current here I want it to be equal to some I naught by 2 times n. Then what can you say about their sizes?
W by n.
So this must have W by n, if this has W and W. So same will happen. So if this is W, this will be some W by n here. Then this will be I naught by 2 times n. And same, this must be MC by n. I'm just scaling the circuit, that's it. So this way I can make sure that this branch doesn't carry a lot of current, but still does the same functionality. So this is often called the replica biasing, because in essence we have created a replica of this branch here, right? So this is another variant of CMFB that you can do.
How is drain voltage is same?
Oh, see, this drain, these two voltages. See, this drain volt. Okay. So first of all, this voltage here, it is set by the gate voltage minus the gate to source voltage.
But this is biased I naught and that is biased I naught by 1.
Correct, but if I have the, see, yeah, W is similar. See, always think of it like this, right? If I have the same current density, my VGS will be same, right? So if I scale my current and scale the W, the gate to source voltage is same. That's all. Okay, so I'll quickly show one last thing and show it. So this last technique also relies on controlling the current in the NMOS branch, assuming that the PMOS is biased. So let's say this is I naught by 2 and I naught by 2. Now the idea here is I'll just show the circuit for the lack of time, not derive it from scratch. See, let us say I somehow make sure that the current here is greater than I naught. Okay, say it is some I naught plus 2 times Ix. Now the point to note is I don't need to know what this 2Ix is. I'll just ensure that this current is greater than I naught. That is easy to ensure. Now nominally I want the current here to be what? I naught by 2. This also to be I naught by 2. Now if KCL has to be satisfied, what should I do?
Current should have another path.
Yeah, now looks like the total current that is coming in is what? What is the current I'm pulling out? I naught plus 2 times Ix. So what should I add here for KCL to be valid? Another path. So in principle I need to have, if I have another current source here, and if its value is 2 times Ix, it is all fine. Okay. But the point is I don't know what this 2Ix is, so I'll vary this current. Okay. Again the principle is same. If this current is not equal to I naught by 2, the common mode will increase or decrease. Now based on this output common mode, I will go and change this current. So in short, I want a variable current source. So I want a current source, but its current needs to be controlled by what is controlling its current? Output common mode voltage. So I want what kind of a current source? I want a voltage controlled current source. What is the simplest voltage controlled current source? Even simpler. Simplest voltage controlled current source. Yeah, it's a transistor. Okay. And I want a transistor that is pushing current in this direction from VDD. So I'll use an NMOS or a PMOS. No, I want a current source from VDD, right? I'll use a PMOS. Okay. So the idea is I'll replace this guy by a PMOS current source. So I'll just show the circuit finally and leave it. Again, here instead of obtaining the common mode using resistors, I'll do the same thing like this. So this way I'll have a current that is proportional to the common mode of these signals. Okay. And what do you think the output common mode will be finally? What is the voltage do you think it will get set to? What is setting the common mode here? Of? Correct, right? See, what is setting the common mode here? Gate voltage of the PMOS, right? So what is the current flowing in the PMOS in steady state? Ix, both carry Ix, isn't it? So what is the common mode? VSG of that particular PMOS at a current Ix. So this again something you can use, but again the issue is the common mode is not controlled by you, it is set by the VGS. Okay, so this is our last variant, and yeah, we'll stop here.